now that we have a way to backpropagation in Python code, let's actually look at that code and enhance that code a little bit, okay? And again, we have already started the coding for neural networks, so this is very important. So what should we do? The first thing we should do is over here, right? This is our code for node from last time, of course, and I can run that, so that's good. Let's say I have a node 3 and then I have another node for 4, right? I still cannot do a plus b right now, can I? Nope, I cannot do that. Why? Because you don't have addition defined for node and node. So let's actually also define addition for the node. And the way you would do that is obviously can do this. Let's not look at all of this code. So oops, there is that. Let me make it a bit cleaner for me to work here. Okay, and so the operator override is known as the add function, self other, okay, and the thing that we want to return is a result. So you add self dot value to other dot value. The children you want is of course self and other, right? And the operation that's we just did is a addition. You return that result, and you want to have a backpropagate function. So backpropagate, you define that function over here. Okay, so let's look at how we can backpropagate an addition. Okay, so for this let's go. Let's take an example, okay, because things cannot be done without an example. So let's say c is a plus b is our example, okay. So we can again visualize this in terms of a tree like this. So c is the addition of a and b, right? That's pretty simple, easy to understand. So that's great. Now remember, when you're doing an addition over here, this guy on the left would be the self, this guy would be the other, okay. So what we want is to find out dc by da. How would you do that? The first thing you need to do, you need to find out dc by dc, right? And then do a chain rule, dc by dc into dc by da. So it does not make sense right now, but if that c appears somewhere in the middle in the tree, then that would make sense, okay. So this term right now would be a 1, but that would make sense later. So this is basically c dot gradient, right? What is this thing? This thing we can calculate, right? And how do you calculate that? You can do a limit h tends to 0, the function of a goes some unit to the right, and then the point at which the a at, and what we want to do over here, we want to reduce that h to a 0 so that the 2 points are very close. Again, this is like easy derivative stuff, right? And just because it's very easy and we've done this like 1,000 times now, I'm just gonna skip some things over here and move fast. So the function of a over here would be what now? A plus b, right? B guy over here is a constant. So let's do the same thing for a plus h. You'll get a plus h plus b. A plus h is basically like a in that case. So let's go. Limit as h tends to 0, a plus h plus b minus a minus b by h. A b goes away, a b goes away. You can do h1 ja h, so you get a 1. Okay, so dc by da, this turns out to be a 1, and this also works for dc by db, right? It will turn out to be a 1. So how should I code that backpropagate function? That is easy. So you should say self dot gradient, right? Self over here is this a guy again, right? This thing over here is the self. So the gradient would look something like this. So plus equal the result, which is c dot gradient. Again, the result in this particular case is this thing is the result, right, that we are expecting. So this over here is basically c dot gradient. So we should do result dot gradient, right? And you multiply that to a 1, and like you don't need to multiply a 1, right? It's obvious. So other dot gradient would also be the same thing. So that should take care of our add problem, right? So let's run this code, and then now we are able to add, right? So 4 plus 3 is a 7, that's correct. We don't have a gradient yet, so let's assign this as a C, and then let's do C dot backpropagate. When we do that, we should be able to see C dot gradient, which is a 1, A dot gradient, which is also 1, because it should be whatever the C's gradient is. B dot gradient is also a 1, so that works correctly. So we have done our add correctly. Okay, let's do the same thing for subtraction. Okay, so how would you do a subtraction? Underscore underscore subtraction, self and other, right? And okay, result is a node, and the value of that would be self dot value minus other dot value. The children would again be self and other, and then the operation would be a minus, return result, and I can do a result dot back propagate. I will assign that a function called backpropagate that I have not defined yet, but I can define that very easily, right? It's just def backpropagate, and let's see what should the backpropagate function be. Again, we come back over here. Let's assume another example. So C is A minus B. Okay, let's figure out what these terms over here are. C over here is basically the result that we anticipate. A over here, you can consider it as self. B is the other guy, right? And then you can also visualize this as a tree. We have done this tree visualization 1,000 times, so there should not be any confusion. The C, A, and B, and this is our operator. Okay, what we are interested in finding out is dc by dA, just basically dc by dc multiplied by dc by dA. This guy over here is again result dot gradient. We are interested in finding this thing over here, so let's find that. dc by dA, what's that gonna be? Limit as h tends to 0, the function of a going certain units to the right, minus the function of a divided by h when h is going to 0. Okay, so the function over here again is a minus b, given that b is a constant, so whatever. So let's do this. Limit as h tends to 0, a plus h minus b minus a plus b. Okay, this thing actually looks like this, and then when you do the remove the brackets, then this will become a plus. So b goes away, a goes away, you left with h by h, you'll get a 1. Let's do the same thing for dc by db, and limit as h tends to 0, the function of b goes certain unit to the right, minus the function of b divided by h. How would you do that? The function over here would still be this guy. Limit as h tends to 0, a minus b, over here is b plus h minus a minus b, okay, by h, which is limit as h tends to 0, a minus b minus h minus a plus b by h. I think a goes away, bb goes away, you're left with a negative 1. So therefore you get this thing. dc by da is a 1, but dc by db is a negative 1, right? And this over here, you can consider that as self, this over here is the other. So what should my backpropagate function look like? Okay, it should look something like this. It should look like self dot gradient is plus equal the result dot gradient, multiply the entire thing by what? Self is a 1, so I don't need to multiply it by 1, and the other dot gradient plus equal result dot gradient, and that should be multiplied by a negative 1. So okay, and that should now work out fine, I think. So let's run that and then do a minus b instead, and then do a backpropagate, and you should see b dot gradient over here changes to -1. A dot gradient should be a 1, c dot gradient should be a 1. So that's working correctly, so that's fine. That's fine. What else can we add in the system? Okay, so let's see it this way. Okay, so if I try to do, let's say, something like a plus 1, okay, it's not backpropagate for now, let's just do a plus 1. Okay, oops. A plus 1 is something that won't be allowed. Okay, this thing is not going away, so let me just manually do that. So I'm not able to do this because a over here is an integer, right? And I don't know how to add that integer, and so it says that integer has no attribute value. So the thing that's happening over here is a plus 1 is basically calling this function, right? And this thing is assuming that the other should be a node, but it's not a node, so it gives you an error. So let's make sure that the other will always be a node. The way you do that is other, right? If is instance this other guy of node. Okay, so if other is an instance of node, then you should just make other as other, so there's no change. Otherwise you should make it a node with that value. That makes sense? So save that, and now we should be able to add. So everything looks fine. I can see that C. So this is addition. A is basically 3 plus 1 is 4. That looks good. Let's do the same thing but for minus, right? It doesn't work right now for minus. So for subtraction, let's go and let's add that over here as well. So we're gonna basically say the same thing, so I'm just gonna copy and paste it. So other, again, I think you can basically do the same thing for division as well. Oops, do I need to paste that? Nope, I didn't yank it enough. Paste that. So now you could do the same. We've done the same thing for division, multiplication, addition, and subtraction. So great. So we should now be able to do that minus. We should now be able to do a multiplication. Should now be able to do a division as well. So everything works out fine. Okay, there's one problem with this, and the problem is that I can do a plus 1, but I cannot do 1 plus a, I think. Yeah, and that's because 1 over here is an integer, and integer does not know how to add a node type to it. So what we can do is, in this class, right, we can actually define a function, right? And the function would be called as r add. I think it's r add self and other. So the way this works is so let's say you're like anything you're adding it to a node, then if the thing, right, so over here integer does not know how to add node, it will look at this function to see if node knows how to add an integer. So over here self would be a, right, and the other would be 1. So I think this is pretty easy. The way you do that is you do self, right, self plus node other. I think that's how you do it, because we already defined that addition over here, and everything else should be fine, right? The values would be fine, because adding, right, even if you do 1 plus a or a plus 1, it's the same thing, so that won't matter. So let's do that, and let's see if our expected output works. It does work, right? 3 plus 1 is 4, so that does work now. We also have to do the same thing for a minus, right? So let's do that for a minus as well. So def r sub, I think that's what it's called, self and other. So over here, the interesting thing is you should do other minus self, right? Because 1 minus a is not the same thing as a minus 1. A over here is the self and 1 is the other. So 1 minus a should be other minus self. and this other should be wrapped in a node. And we can, I think, do the same thing for multiply. Self and other. Multiply is also can be done as self times the node of other. This should work. And def underscore underscore r true div underscore underscore self and other. So if you try to do something like 1 divided by a, and then the way you should do it is node of other divided by self. Okay, so now this would work, right? That's working fine. 1 divided by a should work. That works fine. Multiply works. So good. Now we have basically added all of these functionalities to our node, and this would make it easier when we actually start coding a neural network. This, by the way, is only the engine part for the neural network. Okay, the main neural network, we still have to code that, so that would be done in another video. This was just enhancement to the system that we already have built. So see you.